So now we know how to construct a circuit diagram, right? So let me draw a very simple circuit diagram. I have a cell and I have a resistor, right? And I have joined them. Now there was this scientist. Okay, before going to the scientist part, if I want to know how much voltage has been supplied to this resistor R through this cell which is supplying a voltage of V, due to which a current I is flowing in the circuit, what should I do? In order to know the value of voltage supplied to the resistor R, I'll apply a voltmeter across its ends. And if I want to know how much current is flowing in the circuit, I'll insert a ammeter in the circuit, right? So this reading will give me, the ammeter reading is going to give me the value of current flowing in the circuit. The voltmeter reading is going to give me the voltage which is supplied to the resistor R. Now, there is one very small thing which is right now popping up in my mind, which you guys should know is, I have told you that this part is positive 1, this part is negative 1, right? So obviously I'll draw the current from positive to negative, right? But what was so obvious in drawing the current from positive to negative? Why I'm asking this question is because, see, remember that conductor thing which I told you? These are the atoms or molecules associated, or which are due to which this whole material is made up of, and the electrons which are actually the charge carriers in the conductor, which are moving in the presence of this potential difference, right? So electrons are actually the carrier of current. That means due to flow of electrons, the current exists in the circuit. Now electrons, this electron is actually what? Is a negative charge. So here comes the question, why am I taking the direction of flow of current from positive to negative when I already know that the current which is flowing in this part of the circuit is due to the flow of electrons, and electrons are actually negatively charged. So if these electrons are flowing, how can the negative charge flow towards the negative? That's contradictory, right? Because negative and negative will repel each other. This is a very basic law of physics which we know. Like charges repel each other, unlike charges attract each other. So negative are obviously not going to go towards negative terminal, but we know that current is due to electrons only. So what is wrong here? I'll explain. Right thing is, the current is due to flow of electrons. That is right. This diagram is also right, but that the flow of direction of current is from positive to negative. The only thing wrong here is that we do not take the actual direction of flow of current. We always take the conventional direction of flow of current. So actual direction of current is from negative to positive, because these electrons are actually what? Negatively charged. So negatively charged particles are always going to go towards the positive terminal of the battery or the cell because of the attraction. But we do not, this part, the real direction of current is from negative to positive, but we do not take it. We take the conventional direction of current which is from positive to negative. That is because, see, most of the things in physics are associated from higher to lower. For example, diffusion happens from higher pressure, higher concentration to lower concentration. Wind moves in the direction of higher pressure to lower pressure. Heat flows from one body to another from higher temperature to lower temperature, right? And this positive is actually at a higher potential, negative is at a lower potential. That is why there is a potential difference which is causing these electrons to flow. So electrons are actually flowing in this direction, which is the real direction of current, but the conventional direction of current is from positive to negative. Alright, so let me go back to the topic. We have drawn a circuit diagram where I have taken a simple cell, a resistor, and to know the value of voltage supplied to this resistor, I took a voltmeter. To know the value of current flowing in this circuit, I took a ammeter, right? Now that point is clear. Now, there was this German physicist, the name was Simon Ohm. The complete name was something Simon Ohm, I don't recall it right now. So George Simon Ohm, okay, this was the spelling, George Simon Ohm. What he did, he measured the value of voltage and current and put it in a tabular form in this circuit. But he was not satisfied. What he did now, what he changed in the circuit was, see, kept the ammeter and voltmeter and resistor as it is, but this thing was changed. This is how it went for him. Instead of one cell, he put a number of cells. For now, I'm drawing only 5, okay? And this part was kept free so that it could be connected anywhere between these cells. That means if I connect it here, that means the circuit is completed only with one cell into the picture. That means the voltage has been supplied only by one cell. But if I connect it here, then two cells are in the circuit right now. So the voltage supplied would be twice of the first one if they are of equal value, or the total voltage supplied by two cells. So this time there would be different value for total voltage and total current. Similarly, if I keep on, or if what he did, I am explaining the experiment, what he did, if we keep on changing the value of voltage supplied, he kept getting different values of current. He put it in a tabular form and he draw the graphical relationship between voltage and current. What he saw was very interesting. The obvious fact was, when there is no voltage, there is no flow of current. That means at zero voltage, there is zero current. But with the very first picture, before this diagram, I drew another circuit diagram with that picture into mind. The voltage and I current was something. Suppose this much, at this much voltage I am getting this much current. This is how their voltage and current are increasing according to x and y axis thing. So suppose this is the value, I put a dot here. Now putting all these values in tabular to graphical form, he got a straight line. That means, what does this straight line represent? This represents that voltage and current are directly proportional. And this whole thing is known as Ohm's law. So what is Ohm's law? At constant temperature, that means if temperature is not changing, potential difference is directly proportional to current flowing in the conductor, or current is directly proportional to potential difference applied across the conductor. Both these statements are right. Some books follow one, some books follow the another. Both these statements are absolutely right. So I'll go it again. Current flowing in a conductor is directly proportional to potential difference applied across it. This is called Ohm's law, the statement which I just gave you. So that means V is equal to some constant times current. Current goes to the denominator side. V upon I is a constant, and this constant is known as resistance. Alright, resistance is represented by capital R. So this is how we get a formula for resistance as well. R is equal to V upon I, or V is equal to IR. This is the mathematical form of Ohm's law, but this is not Ohm's law. Many books sometimes give this question for 1 mark. What does this represent? This relationship is a relationship between voltage, current and resistance, but this relationship is a mathematical form of Ohm's law. Otherwise, this is the actual Ohm's law, that voltage is directly proportional to current. Now I've cleared that point out. Okay, so V is equal to IR. I have a formula for resistance, but in order to explain you the physical significance of resistance, you have to go back to the basic concept of current. See, I've told you that resistance is a constant in this equation, right? But I want you to understand what exactly is resistance, what is the physical significance. So I'll make some space for my, and I want you to go back to that part where I explained you that a conductor is having atoms or molecules of which it is made up of, and the real carriers of current are these electrons, right? This is a fact on which both of us agree right now. Okay, now when a potential difference is applied in a circuit, current starts flowing. Okay, current means these electrons starts moving. Now the actual size of electron as comparable to the size of atom is, if this is the size of atom, the size of electron is not even this dot. I don't know if you are even able to see this dot or not, but the size of electron is half of this dot as compared to the size of the atom. Okay, my point is, why I'm comparing the sizes, because if electron is this much small, which is moving in a conductor, they should not have any difficulty in moving, they should go straight. But even at room temperatures, these atoms and molecules are thermally agitated. They are always vibrating about their mean position due to the thermal energy. So these atoms which you are seeing, which are located at a point stationary, they are actually not stationary. They are vibrating in all the directions randomly due to thermal agitation energy, or in simple words, thermal energy. So what is happening? These electrons, they suffer a lot of collision while going from one end to another of the conductor. They get collided, they get collisions, and they go in a zigzag manner. They don't go straight. So this is called resistance. What is this conductor doing? Conductor is offering opposition to flow of electrons from this circuit. This is the definition of resistance. This is the physical meaning of resistance. Resistance is what? It is the opposition offered to flow of electrons by, who is providing? By the conductor, right? Opposition offered to flow of electrons by the conductor. This is called resistance, and this resistance is taken into picture by Ohm's law, using this property that potential difference is directly proportional to I, and that constant of proportionality was called resistance. So we have a formula, and now we know V equals to IR is the mathematical form of Ohm's law, and now we also know what resistance physically signifies.